Welcome all. In last lecture we have seen a level triggered JK flip-flop and a race around condition occurred in the level triggered JK flip-flop when J and K both are 1, and also we have seen how to overcome the race around condition in the level triggered JK flip-flop using edge triggered JK flip-flop. Today we will see the master slave JK flip-flop using which we can overcome or avoid the race around condition which is occurring in the level triggered JK flip-flop. Now this is the block diagram of master slave JK flip-flop. It is the combination of level triggered JK flip-flop and level triggered SR flip-flop, in which the level triggered JK flip-flop acts as a master and level triggered SR flip-flop acts as a slave. The master JK flip-flop and the slave SR flip-flop having a common clock input connected together, but the master JK flip-flop is positive level triggered, and due to the presence of inverter in the clock line, the slave will respond to the negative level of the clock pulse. So when clock is 1, then master is active whereas slave will be inactive as it receives clock 1, whereas when clock is 0, the master is inactive as it is positive level triggered, whereas slave is active as it is negative level triggered. Again, the output terminals, that is Q and Q complement, are connected as an input to the JK flip-flop, that is to the NAND gate of JK flip-flop. This Q terminal is connected to this NAND gate Q complement, and this Q output is connected to this NAND gate. Now we will see the operation of master slave JK flip-flop, which is very similar to that of level triggered JK flip-flop. We will see one by one. In this we have to keep in mind that a clock input pulse is having a train of positive and negative clock pulses. In one clock cycle, a clock contains positive level and negative level, that is positive half cycle and negative half cycle. During this positive half cycle of the clock, master is active, and during this negative clock cycle of the clock, the slave will be active. We are going to see the operation accordingly. Now in the first case, the value of J and K both are 0 and clock is a positive level clock is applied to this circuit. For clock 1, the master is active whereas slave is inactive. As J and K both are 0, in this I will show the values of J and K, both are 0. The outputs of master, that is outputs of JK flip-flop, Q1 and Q1 complement, will not change, which already we have studied in the JK flip-flop. For J equal to K equal to 0, output of JK flip-flop will not get changed. Now in this case, as Q1 and Q1 complement is not changed, which are nothing but the S input and R input of the SR flip-flop, therefore S and R inputs to the slave will also remains unchanged. As soon as clock becomes 0, the slave becomes active and master becomes inactive, since S and R inputs have not changed, the slave output will also remain unchanged, which are Q and Q complement. Therefore, output will not get changed for J equal to 0, K equal to 0. Again, we will see the next case, that is second case, in which value of J is 0 and value of K is 1. Now, when clock is 1, the master is active, the slave will be inactive. As J is 0 and K is 1, the output of master, that is Q1 and Q1 complement will be 0 and 1 respectively. That is, the output of master gets resetted, by which the value of S and R will be S equal to 0 and R is equal to 1, which are nothing but input of the slave flip-flop, that is SR flip-flop. Now, as soon as clock becomes 0, the slave becomes active now and master will be inactive, by which, since S and S is 0, R is 1, the output gets resetted, that is Q becomes 0 and Q complement become 1. So, for J0 and K1, the output gets resetted. Again, we will see the next case, that is J1 K0 and clock is positive level. For J1 K0, during clock as a positive level, the master will be active again, slave will be inactive. At J1 K0, the output of master, that is Q1 and Q1 complement will be 1 0, that is they get set, by which the value of S will become 1 and value of R will become 0. As soon as clock becomes 0, the slave becomes active and master becomes inactive. Since S is 1 and R is 0, the output of SR flip-flop, that is Q, will become 1 and Q complement will become 0. We already know this with respect to variation of S and R, how the values of Q and Q complement will get changed during the study of SR flip-flop. So using that, the Q will become 1 and Q complement will become 0. So the output will get set for J1 K0. Now we will see the last case, which is important, by which we can overcome the rest around condition. In this, J and K both are 1 1 and clock is 1. Now for clock 1, the master is active, slave is inactive. Since the J and K both are 1 1, the output of master will get toggle, means the master is JK flip-flop, and we know the theory of JK flip-flop, in which when both the inputs J and K are 1, the output of JK flip-flop gets toggled, means they get inverted. That is, if previously they are 0 1, they will become 1 0. If previously they are 1 0, they will become 0 1. So Q1 and Q1 complement gets toggled, means they get changed, they gets inverted. As Q1 and Q1 complement gets inverted or changed, with that the value of S and R will also gets inverted or they gets changed. Now as soon as clock becomes 0, the slave becomes active and master is inactive. Since the value of S and R gets changed or inverted, the output of slave, that is Q and Q complement, will also get changed or toggled. Now these changed outputs, that is Q and Q complement, are returned back to the master inputs to these NAND gates. But since clock is 0, the master is still inactive. It does not respond to these changed outputs, which avoids multiple toggling, which leads to the rest condition. Means, as master is inactive, this Q1 and Q1 complement will not get changed, means S and R will not get changed. That means Q and Q complement will not get changed. We get stable output. So this avoids multiple toggling, which leads to the rest condition. Thus master slave flip-flop avoids race around condition using this circuitry arrangement. Now we will see the concept of preset and clear input. In the flip-flop discussed so far, when the power switch is turned on, the state of output Q and Q complement can be anything. That means they can be in set condition or they can be in reset condition. We cannot predict the output status when we turn on the flip-flop. Means Q may be 0 or it may be 1, Q complement may be 1 or it may be 0. But this uncertainty cannot be tolerated in certain application. In some application it is necessary to initially set or reset the flip-flops precisely. This can be practically achieved by adding two more inputs to a flip-flop, which are called as preset input and clear inputs. We will see how these inputs will help to predetermine or to have the output values in the set mode or reset mode. Now we will see the SR flip-flop with preset and clear input. Here this is a basic circuit diagram of SR flip-flop in which only the two terminals are added. This is the equivalent symbol of the SR flip-flop, in which these are the two terminals, preset and clear, which are active low terminals, means they are going to be have a significance when we put a zero value to these both the terminals. Now as there are two terminals, preset and clear, the possible combinations will be both may be 0 0, maybe 1 1, 0 1 or 1 0. We will see the effect of these four possible combinations of preset and clear input on the output of the flip-flop. When preset and clear both are 1, means both are inactive, as both the inputs are active low inputs, then SR flip-flop operates as per the truth table of conventional SR flip-flop, as we have studied the operation in the previous lectures. When preset and clear both are 0, means this terminal is 0 and this terminal is 0, then Q will become 1 and Q complement will also become 1. As we know, at least one of the input of the NAND gate is 0, then its output will be 1. So output of both the NAND gates will be 1, which leads to a uncertain state or which is a invalid state, as the outputs of flip-flops are complementary with each other. So these two conditions are not helpful to set or reset the output of the flip-flop before its operation. Now we will see the next case, that is in which preset input is 0 and clear input is 1, which is called as a preset condition. As preset input is 0, this Q will become 1. Now this clear is 1 and the Q is also 1. The output of Q complement, therefore all the three inputs to this gate 4 will be 1 and Q complement becomes 0, thus making preset as a 0. It will set the flip-flop irrespective of SR and clock inputs. Means when preset is 0 and clear is 1, by which the Q will become 1 and Q complement will become 0. Next we will see the next condition, in which value of preset is 1 and clear is 0. As value of clear is 0, Q complement will becomes 1 and Q will become 0, as all the inputs to this gate 3 are 1. So by making clear terminal as a 0, we can reset the flip-flop irrespective of value of SR and clock inputs. Means the value of Q will be 0 and Q complement will be 1 before we start the operation of SR flip-flop. So in this we have summarized the concept of preset and clear input irrespective of the clock input. When preset and clear are 1 1, then it is going to operate as a normal SR flip-flop. When preset is 0, clear is 1, then flip-flop gets set. When preset is 1, clear is 0, then flip-flop gets resetted.